Right, so for our last week in trig, we're going to take a look at vectors. Okay, there's really a couple different views we can look at with vectors. We can look at vectors as just numbers. We can look at them as sketches, like drawing arrows on paper. And we'll do a little bit of both. So first of all, a vector is used when you want to measure two things. Okay. Does anybody know one of the two things that a vector measures? Yeah? Yeah, magnitude. Okay. In other words, that could be a speed, like of a ball you're throwing. Could be the speed of a car. Could be how hard you're pushing on something. Those are all magnitudes. And how about the second thing it measures? Yep. Yeah, it's a direction. Okay, so if I wanted to model the path of like an airplane flying, I can't just tell you it's going 500 miles an hour. I need to tell you the direction too. Those two things together tell you its path, its speed, and its direction. So some examples you might see are velocity. Okay, another example is force. We're going to do a little bit with force tomorrow. But you can think of a force as like the magnitude is how hard you're pushing, and the direction is, well, the direction you're pushing. You're pushing down, and you're pushing up on something. Okay. And one place we see vectors used quite a bit, where it's really important with making sure we know the speed and the direction of these objects, is with airplanes. Right? So it's kind of hard to see, but all these little gray kind of things here represent planes. And each one of them has a certain magnitude in a certain direction. So if I click on a plane, let's see. All right, so this plane is going from, looks like it's going from Vermont to Logan. And right now it's traveling at, let's see. Oh, its speed is 112 knots. Okay, if you're not familiar with that, that's called a nautical mile. It's a little different than miles per hour. And its direction, I don't know if I see that yet. Okay, because I guess it's a scheduled plane, so it should have taken off 20 minutes ago. But maybe I'm not sure. So usually they tell you the direction too. I don't see it here. Does anybody see it?
It's saying Rutland. Does that mean it's over Rutland right now?
I think that's its arrival and destination. Or destination and departure, sorry. So I think this is where it starts. I think that's where it's going to land. Yeah. So it says it makes sense, about an hour from Vermont to Boston by plane. Let's click. What's the point?
Yeah.
Well, might be faster than driving. You could take a plane from Fitchburg to Worcester. I saw that on here too. It was like 12 minutes.
Really?
Yeah. I bet that's people with their own plane.
People with money.
So here's another one. Okay, it tells us the speed, 384 knots. This one's at an altitude of 36,000 feet. So when we talk about vectors three-dimensionally, that adds another component. Okay? It might look like you've got two planes on top of each other, but in 3D, that might be okay. One could be at 30,000 feet, one's at 2,000 feet. But as far as direction, maybe it's the route. Maybe this has something to do with north and west, like latitude and longitude. I'm not quite sure how to interpret that.
I feel like if you know where they are, you can just kind of take a guess.
Yeah. So you could probably get the direction from that. Right. Okay, but the point is there's tons of these planes. In fact, if you zoom out, it's going to look like the entire country is just gray. Okay, there's so many planes. All right, so it's the job of each air traffic controller at their airport to control all these planes, depending on the speed and how fast they're going, when they took off, when they're planning on landing. They try to keep everything moving smoothly and not have collisions. Okay. So here's an example where knowing the vector for each plane is very important and gets pretty complicated. Okay, now the way they're going to represent all those planes, they actually didn't draw it the way we're going to, okay, we're going to use arrows. Okay, and the reason we can use an arrow is because the longer we draw it, that can represent magnitude. And then the direction we draw the arrow in, that's our direction. In doing things visually, or actually making sketches, does have some important applications, especially if you want to look at the effect of two vectors interacting, like a plane flying south at 500 miles an hour and a wind blowing east at 70 miles an hour. So what's going to happen when the plane is flying and the wind is blowing? The plane's not going to go in the direction it's thinking it's going, because the wind is going to blow it off course. Sometimes you have a wind that blows from behind a plane, okay, and then the plane is going faster. Or you can have a wind blowing it, a headwind, okay, where the wind is blowing right at the plane and it slows it down. So if we sketch those things out, we can kind of see what's going to happen to the plane. Right, so if we have time, we might try a little bit of that. All right, so usually when we draw vectors, we have 2 points. Okay, we have a point where the vector is going to start and where it's going to end. Okay, so in my example, P is the starting point. Okay, we call it the initial point. Q is where it ends. That's the terminal point. So start at P, go to Q. One way you can write that is as a ray, okay, like you did in geometry. Ray, PQ. Okay, and that's fine, but if you're going to be writing a lot about vectors, it'd be nice to have an even shorter way, so we'll talk about that in a second. Now, if I wrote QP, is that the same thing as PQ? Yeah, it's a different direction, okay? If you want to think of it as an airplane, think of flying from Boston to San Francisco, or San Francisco to Boston. That's maybe the same distance if they take the same route, same magnitude, but it's opposite direction. Okay, so it's very important you put the letters in the right order if you're going to use that notation. Okay, but sometimes we might just want to write a vector as a single letter. Okay, instead of using 2 letters, just use 1 letter. Okay, especially when we have a picture. Now, what's the problem with using a letter to describe a vector, do you think? What else do we use letters for? Yeah? Yeah. We use them for variables, and usually variables that represent numbers, not vectors. So if we're going to represent a vector as a single letter, there's 2 ways you can do it. Okay, the first way, which is easier for me on the smartboard, is just a normal letter with an arrow on top. That means that this is a vector. Okay, vector M. Okay, what is vector M? I don't know. I don't have a picture of it. Or you can do a bold letter. Okay, I show you the bold one because that's how your book does it. Okay, so anytime you see a bold letter, that's a vector. Okay, just for purposes on the smartboard, I'm probably going to do it the first way because that's quicker than going like this and then trying to make it bold. Okay, so any questions on the 2 ways we can write a vector with a single letter? All right. All right, so first thing we're going to look at is adding 2 vectors. You could think of this as like how we could look at if we got wind blowing and a plane flying. What's going to happen to the plane? Well, take the wind, take the vector for the plane, and add them together. And the first thing you also want to understand is when you add 2 vectors together, you get a new vector. Right, so going back to the plane, if the plane is flying, south at 500 miles an hour and there's a wind blowing to the east, 50 miles an hour, what's going to happen is the plane is going to fly off at an angle. It's going to be blown off course a little bit. That new course that the plane takes is a new vector. It's a new speed, and it's a new direction, okay, because of the wind blowing it off course. Okay, so the first way I'm going to show you how to add vectors is purely visual. Okay. And what we're going to do is we're going to line the vectors up so that the ending point of one of the vectors is right on top of the starting point of the other vector. Okay, it's like we're going to connect them. Okay, but you want to connect them so that the ending point is right on top of the initial point. Okay, so just off to the side to show you how that would work. Let's say we had these two vectors and you want to add them together. That's the ending point of one. That's the initial point of the other. Okay, all you're going to do is line them up so that those two things I circled right on top of each other. Okay, so that's step one if you're going to add two vectors together, just to see what it would look like visually. And now the new vector that you're going to get when you do that is found by connecting the starting point, right there, to the ending point, right there. Okay, so if I wanted to know let's get rid of that. What's the answer when I add these together? Line them up just like that, and then draw an arrow just like that. That's the answer. So if we called this V, W, this is V plus W. So for this part, there's no numbers. Okay, there's nothing we're going to be doing numeric yet. Okay, we're just going to draw some pictures and practice doing that. Okay, the reason I'm having you start out with pictures is because a couple of the applications we do tomorrow, you have to draw pictures. It's really, really hard to do this without pictures. Okay, so let's just practice adding these up. If you're using graph paper, you could just sketch that the best you can. But what I would do is try to sketch it so it lands nicely, on grid marks. Maybe go down 3 and right 5. Okay, just make up anything that's similar to that. For this other one, maybe just go right 4. Okay. And when you're on a grid, you can draw it anywhere you want. You can start anywhere, you can end anywhere, as long as it's on your grid so you can see it. All right, so I'm going to take V, and it says to take W and add it on the end. All right, so that's the first part. Line them up. And now how do I get the actual answer? What's my last step? Kobe? Yeah, connect them which way? Yeah, well, I'm going to draw a line. Starting from here to there. Okay, that's your start, that's your end. You know where the end point is. Just follow the path of the arrows. That's the end. So that's V plus W. And that's it. The answer is a picture. Okay. Any questions on that? All right, so let's try this one. Okay, before I do it, does anybody see what's going to happen here? You can almost think of this as somebody pulling to the right, and think of this as somebody pulling to the left, and compare the lengths. They're pretty much the same.
Is it going to just turn into a line?
Well, remember, we got to connect that, where is it? We got to connect the start point to the end point. So if I line these vectors up, what's going to happen with the start point and end point? Yeah,
They'll just cancel each other out.
yeah, they're going to be the same thing. Okay? So line this up with that. That's V. I'm going to add W on the end of it. Now, connect the start point of V, which is right there, you just can't see it, to the ending point of W, which is right there. So now when I connect them, they're exactly the same point. There is no vector. So what we do is we call that the zero vector. Okay, when you add two vectors together, you don't get a number. Okay, you can't write 0 the number. 2 minus 2, that's 0 the number. But when you have vectors that cancel out, you write this, okay, the 0 vector. Or if you want to do this, make a bold 0, that's okay too. Okay, any questions on that one? All right. All right, so anytime you start working with numbers or vectors, there's often a lot of properties you'll look at, like distributive property. Does that work with vectors? Okay, we'll get into some of those, but for today, I'm just going to look at these two. Okay. These properties both work with vectors. Okay, commutative means you can switch the order you do it in and you get the same answer. What's one arithmetic operation that is commutative? Yep, multiplication is commutative. 2 times 5, 5 times 2, same thing. What's one other operation?
Multiplication.
Yep, we got multiplication, very good. We're just double checking that we have it.
Addition.
Addition, 3 plus 7, 7 plus 3, okay? Well, we're going to show that when you add vectors, it's commutative. All right, so the first way I'm going to do it is V plus W. So what I'll do is take V, put W on the end, draw my answer. Okay, that's V plus W. Okay, any questions on that? Now, I'm going to switch it. I'm going to do W plus V. Okay, all that means is I'm going to line them up like this. Take W first, then put V on the end of it. Now draw your vector. Okay, and hopefully if we did this reasonably accurate, they should be pretty close. Yeah, those look pretty good. There's W plus V. Okay, my point is they come out the same. Kind of hard to draw in your notes because I'm moving things around, but if you can understand the idea of what I just did, that's what I'm going for. Questions on that? All right, so commutative, you can switch the order, you're okay. And maybe it's easier to switch the order for some reason when you're adding the vectors. If so, do it. It doesn't make a difference. Okay, and the other property that also works is associative. Okay, with associative, you don't change the order. ABC, ABC. Keep the order the same. We're just going to do something before we do something else. All right, so first way I'll do it is A plus B plus C. All right, so let's start with A. Let's add B on the end. And now I'm just going to draw A plus B. So that was A, that was B. That's A plus B. Now put C on the end of that. Okay, so that's C. And now connect where we started to where we end. That's my answer. Any questions on that? Okay, this part was just A plus B, and then I added C and got that. All right, now let's try doing B plus C first, and then take A and add that on the end. A plus B plus C. All right, so let's see. That's B. That's C. I'm going to draw my line in and get B plus C. So I got that. I can move these back. And now take A, and onto the end of A, add what we just did. Okay, let's draw that. Hopefully that looks pretty similar. Yeah, pretty good. So I'm just showing you the associative property. Works fine. Okay, any questions on that idea? So vector addition is both commutative and associative. When you're adding things visually, may be useful, but then if you're doing things numerically, that's where it becomes even more useful. Okay. Okay, we already saw that when you take a vector and add its opposite, you get the zero vector. Okay, what's the difference between V and negative V? Just the direction. Okay, they have exactly the same length. Like if you were to measure this table, it's like measuring the table left to right or right to left. It's different direction you measured in, but same length, same magnitude. Okay, so that's important to understand. Different direction, same magnitude. In fact, it's not just a different direction, it's exactly opposite directions. Okay. All right, so next thing we're going to do is subtract two vectors, okay, visually. But I want to think of subtraction using addition, because if I can do it that way, I already know how to do addition. I won't need to learn anything new here. So how could you, what if I gave you 4 minus 3? I know it's 1. But what's another way you could think of this problem? Somehow putting a plus sign in there. Mm-hmm. Negative 3 plus 4, or 4 plus negative 3, same thing. Okay. Does everyone agree these are the same? So what I'm going to do is, instead of thinking something as subtraction, I'm going to think of adding the opposite. Okay? That's how we're going to do it. Yeah?
Isn't that how calculators work? They don't actually subtract, they just add things.
This is possible. I think maybe it depends on the kind of calculator, but
For sure, I remember reading that.
could be possible, yeah. All right, so in order to subtract, this is how you're going to do it. Find the opposite of the vector you're subtracting and add. Okay. And what does that do again? Opposite changes the direction. It's just going to flip it around. Yep. Okay, so instead of thinking of this as V minus W, how am I going to think of this using addition? Pretty much do the same thing we just did with the numbers. You could think of it as negative W plus V, or V plus negative W. Okay, that's commutative, right? You could switch the order, it doesn't matter. Okay. All right, so I got V. That's V. Got W. But I don't want W. What do I really want? What do we need? Right, we want V minus W. So what do I got to do with W? right? I've got V. Now I need that. I need negative W. Okay, so if you're doing it on paper, you just draw your arrow exactly the opposite direction. Okay, if I'm going to do it on here, just flip it left, right, flip up, down. That's negative W. Okay, now I can take V plus negative W, and that's my answer. Any questions on that? So when you do subtraction, think of it that way. All right, scalar product. What does it mean to scale something? What do you think of a scale model, scale drawing, scale building? What are you changing when you do something to scale? You're changing the size. Okay, you're not changing anything else about it. All you're doing is changing the size. So when we multiply, when you multiply a vector, okay, by a number, we call that number a scalar. Because a scalar can actually do three things. If we change the size, what's one thing that could happen? What's one way to change the size? It could get shorter. Yeah, it could get smaller. It could get longer. And it can also reverse the direction. That's the only other thing it can change. What kind of number would you have to use if you're going to reverse the direction? You'd multiply by a negative. If you're multiplying by a positive, the direction doesn't change, just the size. All right, so if I've got V and I want 2V, anyone tell me what I could do with V to construct 2V? Yeah, how would I do that? Take this one, all right. I'll make a copy of it. All right. Now what? Well, how could I do it exact on the smartboard? Since I'm just doubling it, I can do it exactly. I mean, I could estimate it, kind of just draw it. Well, what could I do to get it exact?
Put them both together.
Yeah, think of what 2V means. It really means to take a V and put it with another V. Take two of them and put them together. Right? So if I make a second copy, put them together, that's exactly 2V without estimating anything. Okay, now if I want to do something like a half, I'm going to have to estimate that. Okay, unless you had if you're using a computer and you had a function that could shrink by 50%, then I could do that. Otherwise, for this one, I'll just estimate 1/2 V. Any questions on that? All right, let's try this one. Sarah, what's going to happen here when I take V and multiply it just by -1?
We're just going to switch.
Yeah, what's going to switch? Yeah, it's going to point the other way. Okay, multiplying by a 1 doesn't change the length, but the negative changes direction. So this would be the same as -V. So again, I can flip it, and then flip it again, and there's -V. Okay, if you're doing it on graph paper, basically the way you flip something is, let's say you went, let's just make up something. I don't know, let's say you went right 3 and up 1. Well, if you go left 3 and down 1, that would switch it. So you just basically make both negatives. Okay, if you went right and up, go down and left, and switch it. Okay, the last one I'll look at for this is negative 1/3 v. Well, I've already got negative v right there. Just make it 1/3 as long. Okay, this is the time where if I was using numbers, it would actually be easier. All I'd have to do is take both numbers and divide them by 3. Okay. But since I'm sketching by hand, the only way to make it more accurate would be to use graph paper. Okay. Questions on that? All right, so this one's having me add 2v plus 3w. Okay, the way I would do this one is just keep stacking all your vectors together until you finally have what you need. Okay, that's 1v. Okay, take another one. That's 2v. And now on the end of that, just put 3 w's. So there's 1. There's 2. And 3. So I got 2 v's, 3 w's. And then Megan, what do I do to get my final answer?
So we go from the first point to the last point.
Yep. Just connect beginning to end. Let's pull off. And that's 2v plus 3w. All right, so all the drawing stuff, I mean, that's great, but we're going to talk about why drawing can be kind of time-consuming in a little bit. All right, so now I'm going to look at a couple things that are not drawing. Okay, the first one is this symbol. Okay, when you have a vector and you put double bars around it, that means they want the length only. Okay, so it would be to find the length and write it down. It's a number. And it's always positive. Even if a vector is pointing down, just because you measure down, it's still positive. Okay, down has to do with direction. Okay, what would be the difference between the magnitude of x and the magnitude of negative x? George? They are the same. These are the same. Again, direction has no effect on the magnitude. So those two things are the same. If you're measuring a vector and it happens to come out exactly 1 unit long, special name for that. Does anybody remember the name of the circle we studied that had a radius of 1? It began with a U. Unit circle. Okay, so a unit circle is a circle with a radius 1. What do you think a vector is called if it's equal to length of 1? A unit vector. No. Okay, so unit vector, just the name of a vector if it happens to be exactly 1 unit long. All right, so now we're going to start to get away from some of the sketches. Okay, sketching's fine if you really want to visualize something, but the problem with sketching is it can get very big. Okay, you could go off the edge of your graph paper and then you got to start over. So we're going to do some things that don't rely on positioning stuff so carefully. And the first way we're going to learn how to write a vector is what's called an algebraic vector. And it almost looks like a coordinate, except what's different? Yeah, you're not using parentheses, you're using these brackets. Okay, so a vector is written with these angle brackets, two numbers in between with a comma. Okay, I'm going to explain what those numbers are. Okay, those two numbers represent what we call the components of the vector. Okay, every vector is usually made up of two components. For this vector, there's a component that's going right, and there's a separate component going up. Then when you put the two together, you get this vector in black that's right and up. Okay? Well, instead of drawing it, what we're going to do is list the horizontal component, how long it is right there, and the vertical component we're going to represent as a number right there. Right, so what these components basically tell you is how far left and right or up and down you go. Okay, so A tells you from an initial point, go, I'm just going to make this up, 3 units right. Doesn't tell me where the initial point is. I can start anywhere I want unless they tell me to start in a certain spot. So start somewhere, go 3 units right, and then B tells you up or down. If B is positive, we go up. If B is negative, we go down. For this one, I'm just going to make up a number. Let's say we went up 5. Okay, so that's the vector right 3, up 5. From the initial to the terminal. Okay, so you're just going to write it as 2 numbers. Okay, let me draw that same vector down here again. Okay, I can start anywhere I want. I do have to kind of plan ahead if you're going to sketch it, so I don't go off the edge of the paper. But we could start here and go up 5. Okay, I could start over here, go right 3, 1, 2, 3, 4, up 5. If all the directions said was to sketch this vector, both of those are fine. But where do you think the best place to put your starting point is? Yeah, at 0, 0, which is the origin. If you have a choice of where to start, I'd prefer you always start at the origin. Okay. And if your vector does start at the origin, that's called a position vector. Okay, so on the above pictures, the only one here that's a position vector is that one. Okay, I'm just going to draw one more. Now, sometimes what they're going to do is give you the coordinates for a starting point, give you the coordinates for an ending point, and they want you to come up with something like that. Okay, let's try that on this one. Okay, we already know the answer. Okay, this is vector 3, 5. But let's say all they gave you was the coordinates for where it starts. Okay, Emily, can you give me the coordinates for, I'll just make this in red. No, I won't. Just point. Can you give me the coordinates for this vector? Just where it starts.
It starts at 3.
Get rid of all those. So we go right how many?
So it starts at 5.
5, comma,
It goes up
just that point.
1.
Yep, so it starts at 5, 1. And it ends, it's a little harder to see. Leah, where does this end?
7,
Yep,
6.
7, 6. All right, so we know where the vector starts. Okay, we know where it ends. And we know that this is the answer. Okay, normally you wouldn't know this ahead of time. What can you do with those coordinates to somehow get 3, 5 as your answer?
Oh, that's me.
Yeah, that's what I'm checking. Is that right?
No, it's 8, 6.
Yeah, it should be 8, 6. Thank you. Does anybody see what we can do to somehow get a 3 and a 5 out of those numbers?
Is it subtract?
Yeah, just subtract them. Okay, so we got 8 minus 5 and 6 minus 1. What we just did here is we figured out how far left and right and how far up and down. We have a right 3 and an up 5. Okay? That's how you figure out what your vector is if you're given coordinates.
Don't do anything after that.
That's it, you're done. Okay, so to find your position vector, subtract your x's, subtract your y's, just like we just did, but it is important that you subtract initial, terminal minus initial. Terminal minus initial. Okay, what would happen if you switch the order you subtract in? What would it do to the vector? If you switch this order around,
The vector would be opposite.
it would change the direction. It would come out the opposite of what you want. Okay, so make sure you always do this order. Right, so our last example is going to be just to find basically what's the horizontal component, what's the vertical component, and write a position vector. Okay, so the first thing we want to do is x2 minus x1. Okay, if you need to, you can label everything. Okay, Kobe, what's x2 here?
X2.
Yep, x2 is 4. Okay, Cooper, what's x1? -1. Okay, and then we need y2. Brianna, what's y2?
6.
It's 6 minus y1, which is 2. Right, so George, what's the vector that I get here? 5, 4. That's it. Okay. So if you're going to sketch it, you can pick an initial point anywhere you want. Just go 5 units to the right, 4 units up. That's the terminal point. Okay. Any questions on that? All right. All right, so the homework tonight, it's all evens, okay, except for number 1. It's on page 344. 1, 8 to 22 even, and 26 to 32 even. Okay, make sure on 26 to 32 do not follow what the directions in the book are. They will not make sense. Make sure you do what I'm writing.